This is our last short video, and it ties a lot of things up that we've been talking about throughout the course. We just spoke about the right side of the storm and the storm surge, and I wanted to talk to you a little bit about that in terms of what happened during Sandy back in 2012. You may recall that Sandy made landfall in New Jersey at Atlantic City, and Atlantic City was hard hit. And it wasn't the hardest hit. As long as you may recall, places like Manahawkin, Seaside Heights, Union Beach were just devastated by the storm. And you know what? They were on the right side of the storm in the path of travel. So we talked about the accumulative wind speed and the surge that's associated with that. And I wanted to go over that with you a bit. So what I wanted to mention is that you have a normal sea level, which can rise at high tide, as what happened with Sandy, came in at high tide, plus a storm surge on top of that, and waves being driven in on the right side of the storm, and suddenly you have devastating flooding. So I wanted to really make sure that you understood that, and just to prove it to you, look at the right side of the storm and the wind gusts during and as Sandy hit in. Clearly, you have wind gusts here that are higher on this right side of the storm than on the left side of the storm. And in fact, what I'm going to show to you next about Union Beach, right around here, 78 miles an hour in here. And look at the devastation that is really well known in Union Beach. There's New York right in the background and the Verrazano. So you can see that those 78 mile an hour winds tore apart homes in Union Beach. Now, just this past week, NOAA released a new report warning about September and October in the Mid-Atlantic Basin for hurricanes. And in that report, they cite the Atlantic multi-decadal oscillation. Now, the decadal part of that stands for decade, and this is a temperature change from warm to cool to warm in sea temperatures, in ocean temperatures, that goes from warm to cool to warm over a 65 to 80-year cycle. We're just starting to understand this natural oscillation, and we're trying to put it all in context. And what we know is that we can plot out these oscillations only for about the last 140 years. In some cases, we can plot out oscillations over thousands of years, but we're just starting to study this. As you know, atmospheric science is a new science, and we have currently been in the warm cycle of this oscillation since about 1995, and that has corresponded to successive excessive hurricane seasons, one right after the other. So what this says is that since 1995, the ocean temperatures have been increasing, particularly over the North Atlantic, but also off of the coast of Africa. And we're really looking at this area because this is where the ITCZ is located, the Intertropical Convergence Zone. And when we note that temperatures are warmer in this area, they fuel that stationary front in the area. So my question to you is, how does warmer water impact hurricane formation and hurricane structure? That's not a tough question for you at this point, but think about it and go through it in your head. And how does warmer water impact hurricane formation and hurricane structure? That NOAA article also looks at surface trade winds and wind shear as a result of warmer ocean temperatures. So what they are saying is that in here you'll see that this warmer water, especially off the coast of Africa, is resulting in weakened surface trade winds. Now, why would that be so? You know what causes wind. You know what the primary driver of wind is. why would those surface trade winds weaken with warmer water? Think about that. And as a result of those weakened surface trade winds, you are going to have less wind shear in the environment. I think that you know that those two things will go together. But my question to you is, why will the warmer water cause the weaker surface trade winds? And lastly, to bring it all together for you, there's another factor in the hurricane seasons that they're predicting, and the multi-decadal oscillation. During the years when the multi-decadal oscillation produces warmer water in the Atlantic Ocean, we tend to notice that the summer West African monsoon is enhanced. There's more rain coming into West Africa than normal during their monsoon months from June to August. So my question to you is, think about those weaker trade winds and think about where they're located and how weaker trade winds might influence a stronger West African monsoon that you see here. These are the winds that bring in the stronger West African monsoon. These are the northeast trade winds. So how do you think weaker northeast trade winds might develop a stronger West African monsoon? And in turn, I think you'll see that a stronger West African monsoon indicates some really low pressure areas along the intertropical convergence zone. You can see it right along here, the ITCZ. And if you have low pressure areas all the way through Africa and into the Caribbean for that ITCZ, it's going to lend itself to more frontal wave action and more cyclonic development. But my question to you is, what's the interaction between the northeast trade winds and these stronger monsoons? I want you to think about all that together and put it all together for yourself. I hope you've enjoyed this course and you've learned a lot about meteorology and the basics of the scientific method and how to think critically about what you're hearing in terms of climate change, climate oscillation, and you'll explore this more in the future. Thanks and take care.